Hi, so I'm Matt. I'm going to be presenting about Stitch, which is some recent work that we've done on learning DSLs for program synthesis. So in program synthesis, in general, you start with a DSL, which is some library of primitives, and your synthesizer can automatically assemble these primitives into programs that meet some specification that you give it. But where does this DSL come from? Well, in practice, it comes from some hardworking grad student carefully designing the language so that it's expressive enough to write down the solutions that you care about, but that it's not so bloated with unnecessary primitives that it's difficult to do synthesis at all. So we're interested in learning this DSL. And there's actually some prior work, DreamCoder, that approaches this problem. So in DreamCoder, you have a set of synthesis problems you want to solve, and an initial DSL for synthesis that's very simple and low level. And if you try to solve problems, you're probably only able to solve a handful of the easier problems in this set. But what DreamCoder does is they send those solutions over to the abstraction learning phase, where you look for common structure in the solutions and define new primitives for your DSL that capture this structure. And we'll look at that in detail in a second. But at a high level, you're basically extending your DSL and then going back to the synthesis phase again, this time with a better DSL that can hopefully solve even more problems, leading to this virtuous cycle of building up a better and better library and solving more and more of these problems. And by the way, there's actually a long line of AI research that DreamCoder is building on that uses the idea of abstraction learning for synthesis. Now let's take a closer look at the abstraction learning step. So imagine you have a set of tasks in a simple arithmetic domain like these. These are specified by some input-output examples, and we could ask a synthesizer for solutions to these tasks in a lambda calculus with some basic DSL. Now, the details of these programs aren't too important, but what is important is that they all share some common structure. They all involve adding something to 2 times something else. And you could actually write this common structure as a function like so. And furthermore, if this function f were in our DSL, we could actually much more concisely express these programs by deleting the common structure and replacing it with a call to the function. And in this way, we've made our set of functions much more concise, and therefore easier for most synthesizers to work with, to synthesize. And furthermore, we're hoping that f is going to be useful down the line when we're solving new problems, and thus we can iterate this cycle to build up a library of primitives. And DreamCoder, so this is all, so DreamCoder actually shows very cool results for this as well. So for example, starting from a low-level list manipulation domain with things like map and fold, DreamCoder can learn abstractions like filter, maximum, nth largest element, and these allow it to solve pretty complex problems like list sorting fairly concisely, while otherwise they would require, something like this crazy lambda calculus program that, a normal synthesizer just could not directly synthesize. So these were some very cool results from prior work, and we actually aren't the only ones to think that they're cool and try to build on them. So earlier in this session, you saw Babel, which focused on broadening the expressiveness of library learning so that you can capture an even richer set of abstractions. And now we're going to look at, and now in this paper, Stitch, we're building on DreamCoder with a focus on scalability. So we're bringing DreamCoder down from taking minutes or hours on problems to the order of milliseconds. So scalability really is a big issue for DreamCoder. And let's take a look at why. So in that abstraction learning step, if DreamCoder wanted to find the common structure between these two problems, it would do a series of refactorings using lambda calculus identities to expose the common structure as a common subexpression. And the issue with this is that DreamCoder is also considering 10 to the 14 other ways of rewriting each of these programs. And so this is a completely intractable search space. DreamCoder tries to tame it using version spaces and egraphs, but ultimately it just still faces massive scaling problems. So it ends up taking, some of the harder benchmarks, it takes up to 9 hours to do a single step of abstraction learning and using 0.5 terabyte of RAM. So the problem is that DreamCoder is slow and memory intensive. And for the rest of this talk, we're going to look at our approach, and then we'll take a look at the evaluation. So in Stitch, we're looking at making abstraction learning actually scalable. So first, we need a notion of what even is a good abstraction. So as we saw earlier, if you have a corpus of programs and some abstraction for common structure in those programs, you can rewrite them in terms of that abstraction. And our utility metric that we're going to use is actually going to be the difference in size. So how much smaller can you make the corpus when you rewrite it? And some useful intuition for this is that it's roughly going to be equal to the size of the abstraction f times the number of places it appears. So in this case, it has a size of 7 because there are these 7 blue nodes. It matches at 3 locations, so its utility is 21. And the intuition for that is that there are 21 blue nodes on the left here because the size times the number of matches basically tells you how much common structure you get to delete. Okay, so we're going to approach finding a good abstraction as top-down synthesis. So we start with just a whole, and we make a choice for how to expand it. So we could expand it, for example, into an application of a whole to a whole. Now at this point, it has a size of 1, and it matches at these 16 locations on the right. And we could continue to make choices about how to expand each whole. And as we do so, our abstraction's going to be growing larger and larger, capturing more common structure, which will increase our utility. But it's also going to be becoming more specific. So it's going to be matching at a subset of the locations at each time, which is going to bring the number of matches down and thus the utility down. So the search problem here is really balancing this trade-off between the goal is to grow the abstraction as much as possible while still matching in as many places as possible. And you can approach this, for example, through a naive top-down search, just enumerating everything, but that's actually going to end up being about as slow as DreamCoder was in the first place. So our approach to this problem is going to involve some more aggressive pruning. So we're going to take a branch and bound approach to this. Now, branch and bound in general is a high level, as an enumerative search strategy, but with aggressive pruning based on upper bounds. So as a refresher, at each step of a branch and bound search, you look at all the different ways that you can expand the current search state. And some of these subsequent search states are going to be completed states that can't be expanded further, in which case you update your log of the best state that you've seen so far. Other states are incomplete and can be further expanded. And finally, most importantly, some states are incomplete, and you can also bound the maximum utility in this branch of search to be less than something that you've already seen. And in that case, you can actually prune the branch of search. And defining this like sound and quick to compute upper bound is really the core of implementing a branch and bound algorithm. So mapping this framework onto our problem, we start with just a single hole as our initial state, and completed states are any sort of abstraction that doesn't contain any holes. And then incomplete states are abstractions with holes. And if we run this for long enough, we're going to end up with a best so far that's equal to that optimal abstraction that we want. Right, but the question here is, what is our upper bound? Well, let's look at an example. So say we want to upper bound the utility that you can obtain by expanding this abstraction in any way. If we look at where it matches, it appears at these 3 locations. And here, I'll just put boxes around these subtrees. And basically, since as we expand this abstraction, it gets more specific, it's never going to match anywhere outside of these 3 match locations. It's only going to be able to grow to capture more common structure within the match locations. Now, since our utility is basically how much smaller we get when we delete common structure, one of the, an over-approximation of this utility can be obtained by just deleting those subtrees completely. So in other words, our upper bound is a sum over the match locations of the size of the subtree at each match location. Now, and in this case, right, to make that concrete, we have 2 size 3 subtrees, 1 size 7, so you can add those up to get an upper bound. And then, for example, if we calculate this, but we'd already seen a best so far that had, I don't know, 17 as the utility, we can just prune this branch of search, because we've already found something better than what you can obtain here. And beyond upper bounds, there's actually a lot of other forms of pruning that you can add once you're in this paradigm of doing synthesis to get your abstraction. So see the paper for details, but one of the most important ones we found was the following. If we have an abstraction like this that matches at at some locations in the corpus, and alpha, the abstraction argument, always takes the same input at all of these locations, it's always 2 here, then we can actually just prune this branch of search directly, like immediately on seeing this. And the reason is because we know that in the search space, a better abstraction exists. And it's this one, which just inlines that alpha to be a 2. This is a slightly larger abstraction, and it matches at all the same locations, and you can, for any way of expanding the abstraction on the left, you can also expand the abstraction on the right in the same way to get something that's just strictly better. So this is our high-level approach, framing abstraction learning as synthesis, and then doing some aggressive pruning on it. And now let's look at what it buys us. So we find that these changes actually make a huge difference in practice. So on the left, we have a graph of memory usage with DreamCoder in orange and Stitch in blue. This is a log scale graph, and so we see that Stitch is around 100 times more memory efficient, so often using megabytes where DreamCoder is in the gigabytes. And also in terms of wall clock time, the difference is even greater. This is another log scale graph, and here we see improvements of between 1,000 and 10,000 times in runtime. So here we're going from taking many problems that DreamCoder would take minutes on, we can solve in a couple of milliseconds. And these are all evaluated on benchmarks from DreamCoder. So furthermore, we see that we can actually scale to domains that DreamCoder can't even run on. So this data set of graphics programs from Wong et al. So Stitch can terminate on these programs within, between a couple of seconds and a couple of minutes. Well, DreamCoder, we couldn't even get to run on the easiest programs of the easiest subdomain of this data set, even when we give it hours and like a terabyte of memory. Furthermore, Stitch is actually an anytime algorithm. So you saw that we were collecting a best abstraction so far along the way, and we can actually stop our search early and just return that best so far. And so here's a graph where on the x-axis we have a log scale of the search progress, and on the y-axis we have how close we are to the optimal abstraction. And from this you can see that within around 1% of our total search time, we're already finding, in many cases, the optimal abstraction or a nearly optimal abstraction. So for extra scaling, you can stop the search early. Now, of course, it's important to compare the actual quality of our abstractions to that of DreamCoder. So this is a plot with the utility ratio on the y-axis and and this dotted line, 1.0, is basically both Stitch and DreamCoder getting the same amount of utility, and anything above is Stitch doing better. So we see that in general, we get comparable and often slightly better abstractions than DreamCoder. Now, another part of this project was actually to make abstraction learning a bit more accessible for people to try out and experiment with their own problems. So we implemented Stitch in Rust, but we also wrote a Python library that you can pip install that basically provides bindings to this underlying Rust implementation. And so you can specify your programs in basically like a Lispy lambda calculus. It exposes some functions for abstraction learning. You can learn your abstractions, rewrite your programs, and there are a whole bunch of other features, documentation, tutorial, and everything. So check it out there and let us know what you think. And the QR code's up in the corner there as well. And yeah, in conclusion, we've made abstraction learning much, much faster. So it can scale to new problems and hopefully, some new applications within synthesis and also outside of synthesis. So please try it out. Let us know how it goes. And these are my amazing collaborators. I want to thank them for all their help. And that's it from Stitch. Thank you.
Hey, are there any questions in the audience?
Hello, Xiaokang Chiu from Purdue University. My question is about the utility function. So the general question is, how did you come up with the utility function, or when do we say library is good? And two specific questions are, have you considered the readability or understandability of the library? I know that the size is like an indicator to, well, succinct programs tend to be more reusable and understandable, but did you consider this as a metric? Or another thing is you have size times match. Have you tried other options, or what's the insight behind this formulation?
Okay, yeah. So we have, so here we show this utility function, and we have, so this utility function is basically based on the literature of minimum description length and basically the rough idea that smaller programs are easier to synthesize. But you're right that things like readability and other or even something like optimization in terms of runtime performance would be relevant metrics. So in this paper, we do actually define a space of utility functions. Here I just did this one, but basically, so we support some features like being able to weight different primitives with different sorts of weights. So you can do utility, like getting the smallest program, but relative to different sized primitives effectively, which maybe could capture some of these features. I think in general with utilities, the key to using this is being able to upper bound it. So any sort of utility that you can define like a quick upper bound on might be relevant. And one more thing is, I guess, you could do a search like this to get some proposed candidates and then evaluate them with something like a readability or whatever more precise utility metric you want to calculate. So that might be another path.
Any other questions from the audience?
Hey, great talk, Alex from MIT. I'm wondering, in the original slide that you showed of DreamCoder, at every stage of the iteration, there's synthesis of multiple abstractions, and you showed an algorithm for learning one abstraction at a time. Do you have any thoughts on when you stop adding new abstractions? Do you add all the ones that save you anything? How should you incorporate Stitch into this loop?
Right. So yes, so that's an important question, which is, right, how many abstractions do you learn at each step of this process? And it's important because, right, if you run it just based on this utility metric that you gave it, you might just end up with like, hundreds of abstractions that are very overfit and technically do compress your set of programs a bit, but that aren't actually that useful for synthesis. So what we actually do, well, first off, in terms of our utility metric, we actually include the size of this function f in the set of rewritten programs. And this helps. So really, we're looking at the initial corpus versus the rewritten corpus plus the size of the library itself. So this helps regularize this a bit to make sure that we're not finding, to make sure we aren't just endlessly adding abstractions to our library. But also, in general, depending on your specific synthesizer, you can basically come up with a cutoff criterion that tells you when adding a new program or a new abstraction is going to not be worth it. So each abstraction you add increases the branching factor, which makes synthesis harder. But, you can basically calculate the likelihood of your programs under your synthesizer before and after rewriting to decide if the rewrite was worth it. So that's right.
Okay, well, I think we've officially hit lunchtime, so if anyone else has any other questions, I'm sure Matt would be happy to answer them offline. And let's thank our speaker once again.